Pyrolysis and gasification are not new technologies. Perhaps the earliest use of pyrolysis was in the thermal cracking of crude oil in 1913. Pyrolysis has also been used for the production of chemicals such as vinyl chloride in the 1960s. It has also been used for the production of charcoal through the use of pyrolysis retorts. Each of these technologies are no longer in use. They've been supplanted by more economical technologies. Let us now look at some definitions. Pyrolysis, sometimes referred to as thermolysis, is the rapid thermal decomposition of material without the addition of air or oxygen. Some references define pyrolysis as rapid thermal decomposition in the absence of air, but in reality, pyrolysis of waste involves some oxygen, either as part of the air that may be trapped along with the waste, or even in systems that pull a vacuum to remove the air, there could be oxygen in the chemical composition of the waste itself, as in the case of cellulose. Depending on the amount of oxygen, some combustion reactions may also occur, but if the oxygen levels are low enough, pyrolysis reactions begin to dominate. Now, as you decrease the amount of air or oxygen, a different set of chemical reactions takes place at high temperatures. Pyrolysis reactions are the reactions that take place if no oxygen is present. There is no one pyrolysis reaction, but rather there are many pyrolysis reactions that take place at the same time or in sequence. Let us again take the case of cellulose. The idealized reactions, and here we show several examples, generate products of pyrolysis that include methane, carbon monoxide, hydrogen gas, etc. Note that pyrolysis is endothermic, meaning it does not generate heat, but instead requires heat for the reactions to be sustained. Gasification is defined as the rapid thermal decomposition of material by partial oxidation through the addition of limited amounts of air or oxygen. When some air is added, the byproduct gas from gasification is called producer gas, which has a low heat content. When limited amounts of pure oxygen are used instead of air, the byproduct gas is called syngas, which has a relatively higher heat content. Let us now compare incineration with gasification and pyrolysis. Some gasification systems, the ones that are applied for coal gasification or biomass gasification, use what are called fixed bed or fluidized bed reactors. But there have been gasification systems specifically designed for medical waste. Medical waste gasification systems have a primary chamber with little addition of air, or only using the air that comes in with the waste. This is followed by a secondary chamber wherein combustion takes place. In some gasification designs, the heat from the combustion secondary chamber is used to heat up the primary chamber. These designs are essentially a variation of starved air incineration. There are different types of pyrolysis systems. Pyrolysis can take place at relatively low temperatures, about 750 or 900 degrees Fahrenheit, and for short times. This is called fast pyrolysis or flash pyrolysis, and it is used for biomass and other applications. For medical waste applications, higher temperatures are typically used, around 1,500, 2,000 degrees Fahrenheit or higher. One way of categorizing pyrolysis systems for medical waste is by the energy source that is used. Some pyrolysis systems use natural gas, electrical resistance heating, induction heating, superheated steam, or plasma arc as the source of heat. Many proposed designs today involve plasma pyrolysis. Plasma is the fourth state of matter characterized by highly ionized gases. Because a plasma is a conductive gas, an electrical current can pass through a plasma and generate large amounts of energy. There are generally two ways in which the plasma is generated. A transferred plasma is one where the current flows between an electrode and the waste in its container, which in effect acts as the other electrode, or between one electrode and another electrode in the molten waste. A second method, called a non-transferred plasma, uses a plasma arc torch, wherein the current flows between two electrodes contained within the torch, with a carrier gas flowing between them and becoming ionized to create the plasma. In either case, the plasma that is formed reaches temperatures of up to several thousand degrees. Different carrier gases or gas blankets are used in plasma arc pyrolysis, such as nitrogen, air, steam, or an inert gas like argon. The gas that is used can create a predominantly reducing atmosphere, mainly pyrolysis reactions, or an oxidizing atmosphere, mainly oxidizing reactions such as those found in incinerators. All these technologies fall within a spectrum depending on the amounts of oxygen in the treatment chamber. On the one end are excess air incinerators with high levels of oxygen. On that end of the spectrum are the secondary chambers of starved air incinerators, or the combustion stage of a pyrolysis system or of a gasification process. The levels of oxygen are lower in the primary chamber of a starved air incinerator or in the first stage of a gasification process. The levels of oxygen are even lower in the pyrolysis systems. With increasing levels of air or oxygen, combustion reactions dominate and the process is exothermic, meaning it generates heat. As the levels of oxygen decrease, the pyrolysis reactions predominate and the process becomes endothermic, meaning it requires heat to sustain the process. We have just covered a very basic background about these technologies, which we need to understand in order to explore the environmental issues, which we'll cover in the next section.